Can you all hear me? Okay. Hi, my name is Siddharth, and thank you all for coming to my talk. It's called Treating Network Assets as Scheduleable Resources. So, I'm an engineer on the Amazon EKS team, and in the past, I used to work for the Amazon ECS team, which is yet another container orchestration framework. And even before that, I used to work for a company called Citrix, wherein I used to work on the Zen hypervisor and the open source Zen server tool stack called Zappy. And I have a bit of an agenda for today's talk. I'll briefly introduce CNI and container scheduling before I move on to describe the challenges and the solution we've come up to address these challenges. Let's move on to describing CNI. CNI stands for Container Networking Interface. It's a highly overloaded term in today's world because it means different things to different people. The CNI project itself has multiple revisions of the spec. Spec version 0.3 gives out 3 commands: add, delete, and version. Add is used to set up the container's network namespace. Delete is used to tear down the container network namespace. And version is used to return a list of supported versions of the CNI plugin. There is a new version of the spec v0.4. It defines a new method called check that used to describe the container's connectivity, whether it works properly or not. The CNI project itself also hosts a bunch of plugins. They go all the way from the simple loopback plugin to advanced plugins like Flannel and PortMap. We even see Windows plugins now on the CNI project like WinBridge and WinOverlay. The CNI project also has a library and provides a skeleton to build and develop your own CNI plugins. So to quickly recap on CNI, the CNI project defines a spec, has a library, and also defines base plugins to build your own CNI plugins for development and testing purposes. The CNI project essentially aims to provide connectivity and reachability for containers. The CNI plugin also has capabilities called plugin chaining, wherein you can make one plugin call another plugin to set up the network stack for the container. The CNI project is very useful for developers because it exactly calls one method to set up the stack and one method to tear down the stack. Since the CNI project decouples the network's development from the container runtime and orchestration frameworks, it's actually very useful for customers and developers. Let's move on to see how kubelet and CNI work together. The kubelet is not exactly aware of the pods per se. They're aware of something called as sandboxes. And the sandboxes and pods are loosely coupled and not tightly coupled. The only guarantee we have today is that the kubelet guarantees at least one invocation of the CNI plugin per sandbox. To ensure that CNI and kubelet work together, we need to pass in these mandatory flags. You need to set the network plugin to be CNI. You need to point it to the CNI binary directory and the configuration directory. And in cases wherein you have multiple CNI set up on the same node, we use lexicographic order to determine which plugin to call to set up the stack. And if you now typically see CNI deployments, they are typically daemon sets which have 3 components. There is the CNI plugin itself, and then there is the CNI configuration, and then there is a node level daemon set. So the daemon is a long running process on the node that the plugin invokes to set up the stack. So if you take the case of the Amazon ECS solution, so we have the EC2 instance, and then we have the kubelet, and then we have the plugin itself. So when kubelet invokes the add command, the CNI plugin talks to the network local control plane to get an IP and plumb the routing entries on the node. Let's now move on to container scheduling to see how it works. So this is the typical architecture of Kubernetes. So the control plane consists of 3 major components: the API server, the scheduler, and the controller manager, and they have a data store called etcd. This is just a flow of how pods get scheduled in Kubernetes. So when users create a pod, they send a request to the API server, which then saves state onto etcd. The scheduler watches for unassigned pods and then tries to find a node for this corresponding pod, and then binds the pod to a node, and the state is saved back onto etcd. The kubelet then picks the pod, sets up the container net stack, and then runs the pod for you. The Kubernetes scheduler essentially finds nodes for pods to run. It's complex and feature rich. It has a bunch of features. You can set node affinity and anti-affinity, pod affinity and anti-affinity. It also supports change and tolerations. So the default scheduler typically takes CPU and memory into accounting for scheduling. So as an example, if you see the pod spec, it has CPU and memory limits that you can set on them. So with the Linux kernel, both of these come from the C group subsystem. So typically, CPU is a compressible resource, and it can be oversubscribed. You can use CPU shares to set up your CPU limits. You can also use a combination of CPU quotas and CPU period to get fine-grained control of CPU. And typically with memory, it's not compressible, and when you run out of memory, it's going to kill some processor or container. So how this thing happens is there's something called as an OOM score that's computed, and the higher the score, the more likely you're likely to be killed. Kubernetes also supports custom schedulers. You can have your own scheduler for special purposes and special needs, and the way to use them is to set the scheduler name in your spec. Let's move on now to discuss some of the challenges we are planning to address. Typically, customers use VPCs to launch their workloads, and the VPCs can be simple or complex. VPCs can have public subnets, private subnets, or multiple siders. One of the key challenges is how do you account for networking assets in the scheduling process? Kubernetes follows an IP per pod model, and with this at scale, how do you ensure that it happens? The other big challenge is that with typical CNI deployments, they use L3 networking, and we also have a long-running node-level daemon, which is used to set up the routing entries on the host. Is there a way to get rid of them? And typically, the IAM permissions on the node are really exhaustive because you need to create and delete interfaces, assign and deassign IP addresses on the interfaces. So is there a way to reduce the surface area? Is the next big challenge. So let's move on to the solution. The solution we've built uses extended resources. It uses custom resource controllers. It also uses admission webhooks, and then we now have a CNI plugin to factor all of this into account. So the first component is called the VPC resource controller. This aims to provision and manage VPC resources for the cluster. It's built using Go, so it's platform agnostic and architecture agnostic. It can be built for any platform and for any architecture. The controller also has a flexible resource model, and it has a simple provider interface. The provider interface makes it very easy to add new resources to the controller. Let's look at the provider interface. The provider interface basically has 5 methods. The first is called get resource name, that basically just defines the name of the resource. And then you can basically tweak your warm pool settings for the resource you're planning to create and delete. So the method called init resource pool is for the initial setup of the resource pool for this particular resource. Create resource is used to create a given number of quantity of a given resource on a given node. and delete is just used to free up the resource on the given node. As of today, we have two implementations of the provider interface. We have the ENI provider and the IP address provider. So how this thing actually works under the hood. So the controller watches for node objects and then advertises the node's capabilities. Like for example, in this case, we get node objects, and when we handle them, we get the node's capabilities in terms of networking capabilities, like how many ENIs this node supports and how many IPs for interface can this node support, and we then advertise them as extended resources. For example, in this case, we see that this node has one ENI, and that ENI supports 14 IPs. The controller also watches for pod objects. So what the controller now does is that it tries to find an IP for the pod to consume and annotates the pod spec with the IP to be used. We also have a VPC admission webhook. It is a mutating admission webhook that basically injects extended resource requirements for the pod object. For example, in this case, we see the limits and requests for the pod objects. The CNI plugin itself is fairly simple. It's a simple executable that reads the pod annotations to set up the pod network stack. The plugin also provides connectivity and reachability. Let's go for a quick demo. Can you all see the screen? Is this better? Is this good? All right. Okay, it's very hard for me to see. Okay. Okay, give me a second. Just bear with me. Yep. So in my cluster, I have a 1.11 cluster and I have a bunch of nodes. To make the demo more interesting, we have a bunch of Linux nodes and Windows nodes. Is this hard to read on the back? Okay. So onto this cluster, I've deployed my VPC admission webhook and the controller. So we have the controller and the webhook running for this cluster. Now let's schedule some workloads onto this cluster. So can you read this? So we are deploying a simple server core web server onto this cluster. This is the Windows pod. Okay. We now see that all of these pods are running, and if you describe any of them in detail, you see that the admission webhook has injected a limit of the private IP and a request for the same. You can also see the controller injecting annotations with the pod IP address, and this should match the pod's actual IP, which was set by the CNI plugin for this pod. Since this cluster has both Linux nodes and Windows nodes, you can also schedule Linux nodes on them. This is a simple pod for Linux. So if you apply these, all of these should be running, and we can also scale the deployments. For example, let's scale this to 10 pods. You see a lot of them are running, and if you now describe one of these pods, you now see that this node has advertised an opaque resource called private IPv4 address, and 3 of them are being consumed by the pod we have on the cluster. Any questions? Yes?
Is the limit of IP addresses already considered inside the Kubernetes cluster, or is it something that you have to configure? Because, for example, if you have a subnet /21,
okay.
Is it Kubernetes or the webhook considering the amount of IP addresses available in your cluster? Like, for example, in a /21 cluster, you will and subnet, you will be able to have a limited amount of IP addresses.
So this IP address limit comes from the node itself. Like in Amazon, each instance supports a set number of ENIs, and each ENI has a set number of IP addresses per instance type. So the IP address you see is based on the instance type of your worker node.
Also on non-Amazon, on non-ENI situations, it's very common to have like a limit of 255 addresses per node. So
I just wanted to point out that, for example, when running EKS, you have to be careful with the subnet that you decide to choose. Otherwise, into a limit of IP addresses that you can allocate into a VPC, and then you are basically creating pods that never work because they won't have any networking.
So your VPC configuration is different from the limits you see here. So like your subnet can be bigger or smaller. If you have a really, really tiny subnet, the IP limits come from the instance class and not from the subnet itself.
thank you.
I'm sorry?
Where does the IP address come from?
The IP address is a private IP address from the VPC.
From the VPC?
Yes.
Okay, understand.
So each pod in EKS gets a private IP from the VPC.
And when I change the networks, is this doable on the fly?
I'm sorry?
When I want to change the networks, because maybe I'm running out of IP addresses, I'm switching to a different network scope, is this configurable or is it static?
What's configurable? So configure the subnet.
If I'm changing the subnets or subnet sizes or something like that.
So the limit is per instance and not per subnet. Hi, yes.
Are there obstacles in this design to supporting public IP addresses, or really globally routable IP addresses for pods? I'm mainly thinking about IPv6 for the future, but globally routable IPv4 as well.
So it's going to be easy to scale this model to support IP addresses. You can just have a new provider that gives you public IP addresses instead of VPC private IP addresses, and that's possible with this model.
If I understand your design correctly, yes. I feel I can see that the local IPAM is not really responsible for assigning the IP address. So is it possible that with this design we are completely able to ignore the IP address range assigned to a node and just rely on the controller and the CNI for IPAM?
Essentially, what happens is now we don't need IPAMD on the node because the IP address comes from the controller itself. So you can do away with IPAMD with this model. Yeah.
I mean, that is the only thing. That is the only thing I wanted to confirm. So that's really cool. It's really cool.
Okay. All right. Thank you.
Any more? I missed it.
So it just wasn't a wee bit clear around the limits and the requests. Obviously, they're the same thing because there's a one-to-one relationship there, but does that impact the scheduling onto that? So if you've got a node that's got a ton load of small pods on there, and you run out of your ENI and your IP limits for that node, does that mean the new pods won't be scheduled on there?
So if the node can't support new IP addresses, then your pods will be stuck in pending, but they will now know that you cannot run the pods because they don't have an IP address available for any of the nodes in the cluster.
So just to be clear, they will schedule, they'll just fail. They'll sit in a pending state until some other external action. So you'd need to have like an alert to do that.
So once you add more nodes to your cluster and then you have enough IP capacity, the pods will then continue to run on the available nodes that you have in the cluster.
I think the answer is if they're pending, they're not scheduled. I think that's the question you're asking. They've not been allocated to a node if they're pending.
Yeah, so if I have two nodes, So if I've got two nodes, one that's got two massive pods on it, one that's got tons of small pods on it, and the node with the lot of small pods exhausts all of the IP addresses that are available for that node type, and I go to try and put on another pod, will it schedule it to the one that's got the capacity to be able to do it? You know, ignoring the CPU and memory capacity stuff.
So with this model, we advertise a new opaque resource called IP address for the whole cluster. So when the scheduler tries to find a node for your pod, they'll try to find a node which has enough private IP capacity, and then put the pods on that particular node.
Okay.
Is there a concept of a persistent IP request? For example, if you have a elastic IP bound to a private IP, can you request that you always be assigned to that node on that IP?
I don't think that's possible out of the box because the current design works with private IP addresses from the VPC.
Okay, so you don't consider IP requests when scheduling just the amount of IP address that a pod requests?
Yes.
Okay, thank you.
Any more? We're going over there, or are you just stretching? Okay. You're going to make me run to the back. God.
So what I need to change if I want to start using secondary IP CIDRs, secondary CIDR IPs for the pods?
Could you just repeat the question?
So if I run out of IPs in my current CIDR and add a secondary CIDR, can I start using them in EKS, and what I need to change in the cluster?
So the current controller does not take into account secondary CIDRs, but if you have a node that's in the secondary CIDR range, and then the IP addresses would then be able to come from that range for you.
Thank you.
Just to point about the question that he just did. When you want to add a secondary CIDR to the VPC, so to the EKS cluster also, because you are running out of IP addresses, the VPC ID changes. So I was running into that issue with EKS. So I was creating the cluster with Terraform, and since the ID changes of the VPC, you need to recreate the cluster because you need to assign the new, you have to assign the new ID to the EKS cluster, so I had to recreate the EKS cluster. Is that possible through the Amazon console to just configure the VPC so it will be reconfigured? So I mean, is it necessary really to recreate the EKS cluster when you add the secondary CIDR to the VPC, so the ID changes?
This might be a little detail. Maybe you should just go to the Amazon booth and ask that question. And a little bit down in the weeds, I think, for the big audience.
The current controller does not take into account secondary CIDR ranges yet, but we will add support for that soon.
Not again.
I had a question. In principle, would your current code be adaptable to some other cloud platforms or some native, VM-based or clusters? Or is it sort of Amazon-specific at the moment?
So I think the controller is a very general purpose and extensible. So you can just add a new provider or whatever resource you want, and then make it register with the VPC controller, and then things should work for you.
Thank you.
Where can I find it?
What do you mean?
Where can I find the code on GitHub?
So as part of the Windows public preview for Windows nodes, the controller and the webhook are already available on GitHub. Like at least the way to set them up have been there on the instruction set, like on the README file. So let me bring that up. So if you look at, this is a doc for EK support for Windows nodes. So this walks you through setting up the VPC controller and the admission webhook and how to set them up in the cluster for you.
Cool, thanks.
Is it possible to get that URL a bit bigger?
The GitHub URL.
GitHub.com/AWS/containers roadmap. Any more questions? Okay, well, thank you very much, Siddharth.
All right, thank you.